Hi, and welcome back to our module on acid-base chemistry. This is Matt Ross at Colorado State University, and today we're going to be working on solving acid-base problems. So by the end of this video, we're going to sort of deepen some of the knowledge we have from those crash course chemistry videos, and we're going to do that by solving for pH given concentrations of strong and weak acids. And we're going to understand how equilibrium constants, or KEQ, are used in acid-base reactions. So just a reminder, the equilibrium constant KEQ, or sometimes abbreviated KC, for the equilibrium reaction AA plus BB to CC plus DD is this equation, and it's the reactants over the products, and it's the activity of the reactants over the products. And activity just means, if you look at A here, the square brackets always mean concentration, and it's the concentration of A raised to the activity of A, and A would just be sort of the number in front of an equation. So if you had like 2 moles of hydrochloric acid added to a reaction, for example. And so this equilibrium constant is really present throughout all of chemistry, but it's also a really important one for acid-base chemistry specifically. So when we use these equilibrium equations in acid-base chemistry, there's a couple things to remember. First of all, strong acids donate all of their hydrogen ions and bases all of their hydroxide ions. So we can make some simplifying assumptions that make working with those strong and weak acid, or strong and acids and bases, a lot easier. Second of all, weak acids donate and accept protons depending on the pH of the system. So if you add a weak acid to a pure water system, you'll get one reaction, but if you add it to one that already has a pH of like 3, you'll get a really different reaction. And for acid-base reactions, we can simplify KEQ to something called Ka or Kb. And the simplified form of this equation is just that Ka equals the concentration of the conjugate base times the concentration of the conjugate acid divided by the concentration of the acid added to solution. So this is just sort of like a key acid-base simplification of the equilibrium equation. So let's just go ahead and work through a strong acid example. We're just going to work through the hydrochloric acid example. So we add hydrochloric acid to solution, and it forms hydronium ions and chloride ions. So if we add 10 to the negative 3 moles per liter of hydrochloric acid to pure water solution, what will the pH be? So when I get these kinds of questions, what I would first do is just write down the key information. So we have the reaction, which is HCl plus H2O, and that's in equilibrium with H3O plus Cl minus. And here we get to start making some of our simplifying assumptions because of the way we know strong acids and bases work. So basically, we can assume that all of the hydrogen from this HCl, it all goes to here. And all of the chloride goes here. And so we can sort of cancel out this. So we don't have to worry about the concentration of hydrogen chloride or hydrochloric acid. We also make the simplifying assumption that H2O equals 1. And so then now, all we have to do, we don't even have to go to the pK, to the equilibrium equation, because we know that all of this reacted. So we know we started with HCl concentration that equaled 10 to the negative 3. I don't know why I added the caret, but I did. And because we know it reacts completely, we know that then the concentration in the final solution of hydronium ions, or of acidity, is also 10 to the negative 3. And the concentration of chloride ions will be 10 to the negative 3. And so when the question didn't ask for the concentration of hydronium ions, it asked for the concentration, or the pH. And so if you just recall from those videos, pH is simply the log base 10 of the hydrogen ion concentration, or hydronium ion concentration. And just to be clear, you'll see this written both ways. You could write this equation as H plus or H3O plus. I just did H3O plus here. So if we did log base 10 of 10 to the negative 3, we'll get a pH of 3. So the pH for this solution after we add the strong acid will be 3. And again, we didn't have to resort to the equilibrium equation because we could make some simplifying assumptions that this reacted completely. And so all of the hydrochloric acid was reacted and there was none left, and so we didn't have to do any calculations. And as you see, when we work with weak acids, we can't escape needing to use the equilibrium equation from earlier. So we'll work through one of those next. Okay, now that we solved that relatively simple strong acid example, we'll move on to solving for a weak acid, which is a little bit harder. Once I get the thing going. Okay, so we'll just use an example of using acetic acid. So if we have this equation where we add acetic acid, and let me get the pointer over here, which is an organic acid, and we add it to water, and then we get the hydrogen ions over here, and then the conjugate acetic acid over here. And so we have this reaction has a pK of 4.75, and we're going to add 10 to the negative fourth moles per liter of acetic acid. And just remember we have this Ka equation. And so I'll switch back to hand drawing and we'll go ahead and solve for this. Okay, so once again we'll just start by writing the equation out. So that's CH3COOH, acetic acid plus H2O is in equilibrium with acetate. I couldn't think of that word earlier. And hydronium ions. And the pKa is 4.75 for this equation. And the concentration we added of acetic acid was 10 to the negative fourth. So I'll just put that here, 10 to the negative fourth. Okay, and so now we are just going to plug those sort of into our Ka values. So again, pKa is just the log, so we're going to raise that to the 10th power to get the actual Ka. So that's 10 to the negative 4.75. That's a 4. And that equals the concentration of acetate, which we don't know. So we'll say, I'll just abbreviate that as AC for acetate. And then the concentration of hydrogen ions, which again we don't know. But we do know that these two are going to be equal because of the equation we have up here. So the concentration of acetate is equal to the hydrogen ions because all of the acid comes from our weak acid, the acetic acid. And that's all going to be divided by the concentration of our acid that we added, which I'll just abbreviate A for acid. But that's going to be minus some amount, and that amount is actually going to be the concentration of the hydrogen ions, which is also equal to the concentration of acetate. So we'll just say minus AC here. And then to make this a little bit more sort of algebraic, I'm going to go ahead and convert this to just more mathematical notation that you would probably think of as easier. So we just said these two things are equal. Let's call them x. And so x times x is x squared. And then that's going to be divided by the concentration of the acid, which we called A. And that's going to be also minus x. And we actually know the concentration of the acid, so we can go ahead and do even more simplification. And we can say the Ka equals x squared over 10 to the negative fourth minus x. And if you're seeing this and you're thinking, oh my gosh, we're going to have to solve for a quadratic, that is true. So we're going to just move this over here and sort of finish off our algebra. And we'll do that by multiplying out this part of the equation to move over here. And so then we'll get 10 to the negative 4.75 times 10. Oh, I'm going to run out of space. Maybe I'll just flip over. So we have 10 to the negative 4.75 times 10 to the negative 4. That equals x squared. And I forgot to actually do one more piece. So 10 times negative 4.75 times 10 to the negative 4 is the first part of that. And that actually is going to be plus, okay, I'll just delete that. 10 to the negative 4.75 times 10 to the negative 4 minus 10 to the negative 4.75 times x. and that all equals x squared. And then just the final step to make this a solvable quadratic equation is we're just going to move all this stuff. We're just going to subtract by x squared over here. And so we're going to get 10 to the negative 8.75, because if you remember, when you have bases, exponents that are multiplied, you can just add them. So 4.75 plus negative 4.75 plus negative 4 is negative 8.75. And that's still minus 10 to the negative 4.75 times x. And that's all minus x squared, and that all equals 0. And so then, now we have this equation. I moved off the screen a little bit, apologies. And we can go ahead and plug that into the quadratic equation or into a solver, and we'll go ahead and do that and get the concentration of x. Okay, so once we've maybe looked up the quadratic equation again and then solved for it, we get a final answer that x could be two numbers, because if you remember, quadratic always gives you two numbers. But we only want the positive one, and the only positive answer is x equals 3.4 times 10 to the negative 5. Yep, I put 4, 10 to the negative 5. And if you recall, let me find the sheet. We have x again was equal to the concentration of acetates and to hydrogen ions. So this is going to tell us the pH again, and so it's going to be 3.4 times, the concentration of hydrogen ion is 3.4 times 10 to the negative 5, and that's the same concentration for acetate. And so if we wanted to just go ahead and do a log base 10 of that, I'm getting lost in my sheets, that's okay. We can just say log 10 of 3.4 times 10 to the negative 5. And I'll just plug that into my computer real quick. Oops. And we get a pH of 4.45. So again, we added 10 to the negative 4 moles of acetic acid, but it didn't bring the acidity all the way down to pH of 4 because it's not a strong acid, so not all of it reacted. So we only got a pH of 4.45 in this example. So that was the sort of video for today. I just wanted to walk through two of the simpler strong and weak acids in our various classes. I'm sure we'll work through more. Thanks.